we get this following application. We get f of x squared minus y squared equals x is multiplied by f of x minus y is multiplied by f of y. Okay, so notice here, before we get started, I would like to remind you about the additive function. Okay, what's the additive function means? Additive function, if you have a function f of x1 plus f of x2, which equals f of x1 plus x2, like this. Okay, the function f of x is going to be expressed as a is multiplied by x. Okay, this is additive function. Now let's go through the proof before we get into problem. Okay, proof. So the proof, I'm going to consider x as a natural number. I'm not going, because there are too many cases, there is a multiple cases here. So I'm going to consider if x is an integer, x is positive, and x is negative, and x is a rational number, and x is a irrational number. Okay, we are not going through all the cases. I'm just simply going to consider x as a natural number. So for x as a natural number, I'm going to build this proof. Let's take f of 2, for example. I'm going to start with this one, you get arrived to this one. Okay, so get f of 2, which is equals f of 1 plus 1 is the same as we have here. So I'm going to apply this theorem as an additive function, f of 1 plus f of 1. So this one is clearly going to give us 2 is multiplied by f of 1, like this. Okay, let's do this one inductively. So let's assume for all k as a natural number, get f of k minus 1, which equals k minus 1 factor f of 1. Okay, so f of 1 will be replaced with a. Let's put a equals f of 1. Okay, there exists some a which is verifying this one. Okay, so we are going to prove f of k, which equals f of k is the same as 1 plus k minus 1. Okay, which equals f of 1. Let's apply this one plus f of k minus 1. Okay, I'm going to we get f of 1, f of k minus 1 will be replaced with this one, which is k minus 1 factor f of 1. So I'm going to distribute this one and get f of 1 plus k is multiplied by f of 1 minus f of 1. So f of 1 will be cancelled out. I will be left with k equals f of 1. This one is going to give us k is multiplied by f of 1. So we have proven this one. So which means this one is true. If you have this one as an additive function, which is verifying this condition, it's clearly is the function is going to be expressed as a is multiplied by x. Okay, so now let's get rid of this one and move on to our problem. Now let's claim f of x equals c is multiplied by x, where is c is as some real numbers. Okay, so x is a real number. So I'm going to prove this one is going to be expressed as additive function, as we have seen in previous proof. Okay, you know this additive function is an odd function, always f of 0 equals 0. Okay, so let's give x equals 0 and y equals 0 to see what's given us. Let's put x equals 0 and leave y free. Okay, so I get here f of minus y square, which equals minus y is multiplied by f of y. Okay, let's in this case now let's put y equals 0 and leave x is free, so which means I get f of x square, which equals x is multiplied by f of x. This one is going to be 0. Okay, now let's save these two informations and use them in the next step. Now what to do, I'm going to combine these two expressions and extract a new expression. Okay, let's replace y with x here. in the first equation. See, this one is simple, is going to give us f of minus x squared equals minus x is multiplied by f of x. Okay, I just replaced y with x. Okay, it gives us this expression. Now let's combine this expression and this expression. Since we get x is multiplied by f of x in both equations, I'm going to combine these two equations. It gives us another equation. Okay, so let's start in with this one. So we get f of minus x squared, which equals minus f of x, which equals minus f of x squared, minus f of x squared. It's clearly this one is an odd function. So now let's replace x squared with z. I get minus z, f of minus z, which equals minus f of z. So I get this new expression. This one immediately is starting as f is an odd function. Okay, also f of 0 equals 0. Okay, now let's prove this one is an additive function, as we have seen. This one, it seems, is going to be is an additive function because it is verifying two conditions. Is verifying f is odd, which means it's passing through the origin. Okay, by doing this procedure, so we are going to prove this function is an additive function, as we have seen before. Then we move on to the last step where we can identify the function. Okay, I have the origin expression, which is f of x squared minus y squared, which equals f of x minus y f of y. I'm going to move over this one to the left. I get f of x squared minus y squared, which equals f of x. X is multiplied by f of x. X is multiplied by f of x. It's clearly, it was f of x squared, like this. Then replace this expression with f of y squared, because we have just replacing x with y. So I get y f of y equals f of y squared, is the same as I have here. Okay, so which means this expression is going to be f of x squared minus y squared plus f of y squared, which equals f of x squared. Let's put this term and this term together, as I have previously done. So I get f of x squared minus y squared plus y squared. If I'm going to cancel out that, I get f of x squared, which is true. What we have here, as I have previously shown, this was on the form of f of a plus f of b, which equals f of a plus b. Okay, additive function. Now we have shown the function is additive. Now we are going to use these two conditions. We get this fact as we have been shown before, and also we have shown f is additive. Okay, now let's use these two conditions and let's use this equation. So I get f of x plus number 1 quantity square, like this, which equals x plus 1 is multiplied by f of x plus number 1, like this. Okay, to distribute this one first, so I get f of x squared plus 2x plus 1. I'm going to use this condition that I have previously shown, which is additive function. So it's going to have f of x squared plus f of 2x plus f of 1, which equals this one. I also apply this rule on this one here. So I get x plus 1. This one is going to be f of x plus f of 1. Okay, now at this moment I'm going to distribute this one out as well. So I get x is multiplied by f of x plus x is multiplied by f of 1 plus 1 is multiplied by f of x, which is f of x. Lastly, I get f of 1, because 1 is multiplied by f of 1, which is f of 1. Okay, if you take a look up here, this one exactly equals to this one. Okay, I'm going to replace it. So we get x is multiplied by f of x. Also, this one is the same as f of x plus f of x, which is 2 times f of x, plus 2 times f of x plus f of 1, which equals x f of x plus x is multiplied by f of 1 plus f of x plus f of 1. Okay, we will have a lot of cancellations here. So this one will be cancelled out with this one, and this one will be cancelled out with this one, and also this one will be cancelled out down to the 1. Okay, at the end I get f of x equals x is multiplied by f of 1. Thus I get f of x, which equals f of 1 is multiplied by x. Okay, so I have ended with this nice expression, which is true for all f of 1 as a constant. Okay, so thank you for watching. I will see you next video. Bye.